Okay. Uh, Welcome. I think this is on. So today I'm gonna knock out. Well, I already like briefly solved two of the problems recently, but I'm gonna go through four. Um, I'll obviously start with the ones that I did solve, um, and then I'll go through my explanation and reasoning for that, and hopefully I better understand myself, and for anyone watching, understands this even better. So let's begin. Um, okay, so we'll start with linear regression. So there's two ways, right, on DeepML, if I look at problem 14 and 15. So you can use regression, or you can do conduct regression using either the normal equation or gradient descent. So let's start with the normal equation, and let me reset this code. So here we want to write a Python function that performs linear regression using the normal equation. And the function should take a matrix X of features and the vector Y target as input, and return the coefficients of the linear regression model. And then we have to obviously round our answer to 4 decimal places, but in DeepML, we don't care about that. So let's begin. Okay. We'll denote this as, what problem is this? 14 and 15. Okay. So, okay. Here we just have to look at what our inputs are. Okay, so we're given X, which is a matrix, and we're also given a vector Y, which I believe is our output. So, given X, right, and X is some matrix, and then it's going to be an n by n matrix, where, let's see, where I believe that M, M is our training examples, or training samples. So it's basically how many data points we actually have. And then n would be the number of features we actually have, right? And what I mean by features, I think I talked about it in previous streams, but essentially, it's just how much info, I guess for this specific problem, that each data point or training example has, right? So if we think about things like the iris data set, I think there's 4 features, and there's, I think, 150 or 200 flower data points, right? So each flower has information of 4 categories, and then the goal is you want to classify what type of data point or flower it actually is based on the features that you're given, or the feature values that you're given. So that's essentially what this format is when we think about what our input X matrix is, right? So I guess more specifically, a better way to visualize it is, let's say in this case we have 3 vectors, right? So that means we have 3 data points or training samples, and then let's say each vector had a length of 4. That means we have 4 features for each point. And that means we have four values that we need to use to make a prediction on, or classification on what that data point is, or just make a prediction in general. And the good thing is that we're also given another input, which is our y, and it's an n by 1 vector, right? So in this case, let's just say wait, let me think. No, not n by 1, sorry, it would be m. And what this means is y contains like the actual predictive values for our three training examples, right? So if we go back to the iris data set analogy, there would be 150 or 200 different flowers listed in our input. So that means the output vector that we actually use when we train our model would be 150 or 200 by 1 matrix. That's what the dimensions of this would be. And because there's only one output, right? There's not multiple features, so this is always going to be 1. And what that would also mean is that we'd have to transpose this vector to make it a column vector later on when we actually use the normal equation, all right? So now we know what the structure of our data is, right? It's two inputs, our input matrix and our y vector. So let's actually talk about like what the two methods are, right? Well, we talked about the normal equation, and we're doing the normal equation, and now we're eventually going to do gradient descent, right? So there are two different methods, all which lead to pretty accurate results, right? But yeah, let me see if I can find a good source, like normal equation for regression. Okay. It's a direct analytical method to find the parameters for linear regression. Oh yeah, and another thing, right, is obviously we have these inputs, but what's the goal? Like, what are we trying to do with linear regression? Well, we want to find parameters in our model that actually minimize our cost function. And what that specifically means is, say, like, okay, what's the point of, like, us creating a model? We create a model or some mathematical algorithm to compute some predictive values for each data point that we have, right? Let's go back to the iris data set. So we're going to try, we wanted to build a model that actually, like, accurately calculates some outputs value that represents a certain class that the flower is in, right? But how do we do that? Like, what is inside the algorithm that actually makes those, like, accurate predictions? Well, we have things called parameters that actually exist inside the model. Now, the obvious problem, right, is if we just initialize random parameters in our equation, then obviously we might not get, optimal predictions for what that type of flower would be. So we have to find a way to optimize those things, right? So what people discovered is that we build a cost function or some loss function that evaluates how wrong were our current predictions, right? And then we calculate the derivative or the gradient of that loss with respect to each of our parameters that exist in the model, so then we can find some mathematical relationship to discover, okay, what certain parameters, like what value of that certain parameter would help minimize that loss function. And that's the goal for this. Let me see. Okay. I don't know. I'm not sure. I think my stream is like going a little off, but it also could be my AirPods.
Yeah, I'm not sure what it is, but it's whatever. Okay. Anyways, I'll stop using my AirPods. As I was saying, we have an equation for that, right? Or two equations. So for small examples where it wouldn't be computationally expensive, we have something called the normal equation, right? And what this does is it returns us a list using x and y only. It returns us a list of optimal parameters that minimize whatever our cost function is, right? And that equation is denoted as this. So let's say, call this the normal equation. That, I believe, would be the transpose of x, right? Times x on itself, and we take the inverse of that, and then we take that inverse, and then we multiply it by the transpose of x, and then we take that entire result and we multiply it by our y vector. And all of these operations are matrix multiplications. So obviously turning this into a column vector, right? Because this is just an m by 1. We want to turn it a 1 by m vector. Well, we eventually will want to turn it into an m by 1 vector or a column vector. So then it's correctly fit to perform this operation. Okay. So in this normal equation, right, it will, like I talked about, it will return me our, let's say we call it parameter theta, right? Let's say that the vector that contains all our parameters is theta. And how do you know how much parameters you have? Well, it really depends on how much features we have. So if you think about like a simple neural network, right? Let's say we have one input, okay? In this case, we have 4 inputs, right? 4 features in our mini example. All of that will be turned into a weighted sum into our next neuron, right? And then this is what we call a linear model. Normally, right, in neural networks, you also have something called a bias, but for this specific problem in DeepML, both problem 14 and 15 actually, we're going to disregard the bias. So whatever our optimal equation is in our hyperplane, right, in this case is a 4-dimensional hyperplane, it will always be centered at the origin. Obviously in the real world, that's not actually what happens, right? But let's say this is our equation. So we have x1, x2, x3, x4, right? And we want to get to y, okay? Well, our linear model would be literally x1 times w1, right? Oh yeah, and x1 to x4 is the values of the features for whatever training sample that we're on, right? Whatever mth training sample we're on, these are all the features. Plus, and then we repeat this linear combination all the way to the last feature, which is this. And then that is how you compute our y, right? So this, specifically in our problem, is what our model looks like, right? There's not going to be multiple hidden layers in this case. It's just one linear model, and it looks like this. And the goal is we want to find out what the values of w will be, right? Which will return as a list through theta, okay, from the normal equation. But we want to find what values of w actually produce values of y that come very, very close to what this actual y vector, input vector, were given, right? I don't know if I said that in English correctly, but you might, those of you watching might get the point. So, yeah. And then this would be, we want to return theta, which is, in this specific case, for both problems, a 1 by n vector, right? So we know that this is our solution. We're already given the inputs. Now we just have to compute this operation and turn it into code. Okay, so what are the two things we have, right? Well, we have a transpose. We know we have to do matrix multiplication, and we also have to do an inverse, right? So those are the three operations that we have. So now let's actually code it up. So here, okay, using NumPy, right? Well, we can do two ways. We can either do like the pure scratch method, or we could just do, I think we can do this in the one-liner, right? Just using special NumPy operations. The only thing is it would be really tedious, especially like if we just hard-coded like whatever the edge cases or the test cases are for the specific problem in the DeepML website. Doing this inverse operation from scratch would be hard, so I'm going to resort to the linear algebra library that NumPy offers. Okay, so let's start. I'll do the scratch method. Okay, so we have matrix multiplication, and we also have a transpose. So let's start with transpose. So the definition. Let's create a function called transpose, and it will take some matrix M, right? And it will be a list of floats, okay? And then that will yield us another matrix, which is a list of floats, okay? And then now, let's actually write the algorithm for this. So I'm going to stick with what I wrote in a previous stream. For those of you that want an in-depth explanation, this is not too hard, but we can continue. So for C in range of length of M0, right? We'll also create transpose sublist for R in range of M sublist dot append R C. Okay, and then transpose dot append sublist return transpose. Great. So now we finished the transpose function. Now let's actually finish the other function that we're going to write, or the other operation that we're going to write from scratch, which is matrix multiplication, right? So we'll call this matmul, right? And then it takes in what? Two vectors, or not vectors, two matrices. So we'll call it A and B. And then that will yield us, obviously, another matrix. Now, like before, I won't go into an in-depth explanation, but I'm just gonna write the n cube solution or algorithm for this operation. So we'll start with that. For okay, great. Now we actually have the matrix multiplication operation done from this function. I think this is right. Obviously, if I did a typo or something wrong with my logic, then I'll fix that. Right? And then now we also cover the operation using it's this thing, which is, and it'll be np.linealg.inf, right? And then we just type in whatever our matrix is, and that will compute the inverse for any matrix that we actually have. Okay. Going back to our equation, right? So let's break it down into components. We'll start with this one first. So it will be, we take x, we find the transpose, and we make a matrix multiply it by itself. Well, the original x, right? So that would be, let's call it x t times x, right? So we'll do matmul, and then we'll do transpose of x, and then x itself. Great. Now we'll find the inverse component, right? So now we actually have to do this greater component by taking the inverse of what we just computed. We'll call that inf, and then we'll just, it's quite literally np, is it? Yeah, it's np.linealg inf of xtx, right? Yeah, that's what it should be. And then now we'll find this component, and I think that would just be a matmul operation, so we'll just call it like big component equal to matmul of inf, and we also take in the transpose of x. Right. Now we can actually do the bigger component of this expression. And like I said before, we need to, it's important that we can convert this into an m by 1 column vector, right? And the reason for that is because we need to match the number of columns, right, for this vector, or the number of rows of this vector, and make it equal to the number of columns of this big component that we just computed, right? Because that's how matrix multiplication works. So there is a numpy operation or function that I can write for that, but the goal of this exercise is to write everything from scratch, right? So the code isn't that bad. It's just this. We'll call it like ycol, right? Which will be our column vector, and we'll append one-dimensional 1x1 sublist to it, right? So for I in range of the length of y, we'll create a sublist, right? And it's just gonna have one element inside of it, which will literally be whatever the element is, whatever index element we're currently on through y. And then we'll append that sublist onto our y column. So great, now after this function runs, we have our column vector, and then we have what our big component. So our final step would be to return, or no, not return. Well, we will return it, but let's call it, we'll find theta, right? Because theta is our optimal parameters. So we'll do theta is equal to matmul of big component and ycol, which is a column vector. Then we return theta. And hopefully, if I didn't write any bugs, this should be the correct answer. Okay, what's going on? Oh, I'm forgetting a colon. Where am I forgetting it? Line 18. Oh, okay. Oh, typed in transpose, not transpose. Where is that? It's right here. Okay. Oh, Great, okay. So we passed all the test cases. Obviously, I forgot to round it down to the nearest 4 decimal points, but that's fine. But yeah, as you can see, our output's matched. So this is as scratch of a solution as we can produce to solve this problem. But now let's actually write what we normally do, right, in practice. And it's quite literally this, right? So we want to find, right, the transpose of this, right, and it's an inverse. So it will be np.linalg, right, inf of the matrix multiplication of the transpose of x times itself. So it will be np.array of x dot t at np.array of x. So now we have our inverse component, and then now we just need to multiply that, or matrix multiply it by the transpose of x, which is np.array x dot t. Then finally, we have our big this should compute our big component, and then now we just do np.array y. Oops, I accidentally deleted my whiteboard. And this one line should give us the exact same solution that we wanted, if I didn't write anything wrong. But yeah, that's literally it. So you can, for anyone that does this problem, you can write it from scratch. I highly recommend it because I think it puts you into the mindset of actually thinking about every mathematical operation. But yeah, this is a neat problem. So now let's go back to problem 15, right? And we're going to write the gradient descent operation. So I already explained what x and y is, but now we're also given another parameter, which is alpha in our iterations. Okay, so the question becomes, right, what is alpha? Okay, so alpha would be this is what we call something called our learning rate. So let's actually talk about like what the gradient descent equation is, and that is denoted as our new parameter, right? So I talked about how we have to iteratively like update each parameter that exists in our model, right? And in our case, it's this. So there are 4 parameters. We go through each parameter, and using our x, y, and whatever our predictive output was, we use those 3 things to compute some like cost, right? Some gradient, and we multiply that gradient by the learning rate, and we subtract that product from our old parameter to find out what the new parameter is, right? And I know I said it a lot in words, but this is what the actual equation looks like, right? Minus the gradient. Now, the specific the specific equation for this problem, right? Because it's a linear model. We use this thing. It's this exact same format, but the gradient is actually computed by this. Minus alpha, right? Which is then termed as the summation. Okay, so the gradient is computed by this. So it's the summation of each training sample, where m is, like I said, the amount of samples or data points that we actually have for our input. And then we take our model's output, right? So let's just call it a function h, which represents our hypothesis equation, right? So h of x is our hypothesis equation. Okay, so our hypothesis equation would be whatever x I we're on, okay? So it would be this minus, so we take whatever we predict, okay? Then we subtract it, we subtract the actual like y vector output for this, and then we take that difference and then we multiply it with the feature value from our set, okay? And then it's this expression that we're going to sum to the total, right, for each feature sample. Now I know this equation, it's a lot bigger than whatever this was, and there's like a ton of like parameters or components to it, but we'll actually break it down into code and talk about like why it works the way it does. And the other component, right, so we know that we have our x or y, and I already implemented alpha into like whatever algorithm that we're going to use, but I didn't talk about the other parameter, which is iterations. And that is essentially, right, it's just another parameter that tells us how many times are we going to run this like calculation, right? So normally, right, how in deep learning, how this would work, right, is you have something called epochs, and let's say like the biggest models out there, right, people would run it for like thousands of epochs, right, to train the largest LLMs. That's just essentially, when people refer to epochs or training iterations, that's just essentially like referring to how many times are you going to recalculate your parameters based on the previous parameter, or previous set of parameters, or previous, like people would refer to it as like the previous time step, right? When we talk about optimization algorithms. That's essentially what iterations is. So whatever algorithm that we were going to write, we're just going to insert that into another outer for loop, which just runs iterations number of times. That's all that is. So we are given, okay, so the problem DeepML, it gives us standard like starter code, which gives us M and N, right? And what is M and N? Well, I talked about that when solving the previous problem, which is just this X, the shape of this X matrix. So we have M data points and we have N features, right? And then Y, and they even reshape it for us, so I don't have to run that like scratch for loop that actually turns the y vector into a column vector. They do this for us through this line, right? And then theta is just some vector, which is an n by 1 column vector that is initialized to zeros through the np.zeros function, okay, with n by 1 dimensions. So what do we need to do? Well, we need a way, we're given theta, right? We're given our parameters, but we also need a way to store the new parameters based on the old information that we're given. So what we're going to do is we're going to create a new vector, which is theta new np.zeros. It will have the same exact dimensions, and the reason why we make another list or vector is because we want to like store the new parameters, right? And then we're going to go based off what this is. I talked about that before, but I'm just going to repeat it again. Okay. Now, the next component, right? So this is going to be like storing new info. Okay. Now, what's the first component? Well, we know that our algorithm is going to run iterations number of times. So we'll write something like for iteration in range iterations. Okay. Great. Now we actually write what our code looks like. The first step to gradient descent. Well, we know that we have access to what our y is, okay, and we know we have access to what our x values are, right? But the question is, what is this value? How do we get this value, right? And we have access to this. That's good, right? And then we're also given theta, which is initially 0 from the starter code. That's good. And we're also given the bounds of the summation based on the x shape. But how do we get this value, right? And like I talked about, this our current model for this linear regression problem is whatever this was. So this model is literally what this is, and then we just write it out, right? It's going to be some vector of y values, and we'll just calculate it. So that's the first step. We want to find our predictive. So calculate predictions. So model predictions. And then we'll calculate each, for each training sample we have, we'll calculate the prediction, and then we'll append it to our output, or predictive outputs. Hypothesized outputs, to be specific. So it will be for, well, we know that we have m training samples, so for I range, we'll call it j. For j in range m, right, we actually need to calculate a prediction, right? So our prediction is obviously going to be 0, and it's going to be the weighted sum from all the feature values for that specific data point, right? So for I in range of n, because we have n features, right, we will do a weighted sum of theta, right? So our w's are going to be theta, and that's what we're going to be optimizing. So whatever iteration we're on, we just take that from theta, which is our old parameters, and we multiply it by our actual x values, right? For that, our feature values for that specific training sample, okay? And then that is what our prediction is, and then we're going to append that prediction to model predictions. Okay, that's all that is. So great. Now we have code that calculates the predictions. What's the next step? Well, now we just have to calculate what this expression is. So the first step is we want to find what the summation is, right? So we have to do some iterative for loop. So that will be for I in range of n, right? Because we want to update n parameters, right? We have n parameters in a model that help us reach m predictions, okay? Just, I know it's repetitive, but the more you think about it like that, the easier it is to write the algorithm. So we start with iterating, right? The goal is for I in range, right? So for each parameter, calculate the gradient, then update the new parameter, and then we want to copy new parameters onto our old parameters. Okay, that's all we're doing, right? And so that's why we did this step, because we do calculate predictions for gradient calculation. Okay. So let's do the first step. Let's calculate the gradient. So we'll need to find what our summation is, right? Our summation term, and that will be for j in range of m, because it's from I to m. We'll do predictions, or it will be model predictions, j, right, minus what the actual output is, and we'll take that difference and multiply it by our specific feature value, right? So now scratch myself. Okay. So now we actually have our summation term. So let's calculate what the gradient actually is, or yeah. So gradient is equal to alpha times our summation, and then we divide all of that by m, right? Oh yeah, there's another I forgot to talk about it. There's another part to this, but we divide this entire product by m. Yeah, so for anyone that was confused, that's why we have this. Okay, so we divide this by m, right? And then now we actually have to update the new parameter. So that is just simply theta new, right, I, right, is equal to theta, which is our old weights, 0, or I, minus the gradient. And then now we actually have to update what our old parameters are, so then we can use those new parameters. Like, we have to copy the new parameters onto our old parameters, so then we can use that new information for the next iterative step, right, for gradient descent. And that would be theta I is equal to theta mu I. And that's that. So we'll see if this works. Okay. And there we go. Yeah, so that is what we actually got. All the test cases passed. And as you can see, right, this is the code that we actually wrote to solve the problem. Yeah, store new info. So let's go over this code again, right? We're given starter code m and n, which is the shape of our input x matrix. We're given y, which is reshaped to a column vector, and then we are given theta, which is, for any problem, always initialized to 0 at the beginning, before we start conducting iterative gradient descent. So the first step that we needed to do was create a new vector that will store the new parameters based on calculations from our input, or our parameters, and whatever our old weights were, right, from theta. Then once we now we actually have to write the algorithm and run that algorithm iterations number of times, right? So that's why we have this outer for loop. And the first step to gradient descent is we want to calculate what our predictions are for that specific. We want to create model predictions, right? So we run that. In the deep learning world, it's just called model.forward, and we store those predictions. Then after that, we want to calculate the gradient, which is run from this for loop. And then for each parameter, we calculate what the gradient actually is, and then we update that based on whatever that parameter is. We update that specific parameter, and then we copy the new parameter that we just calculated onto that same index of the old parameter list, right? And once this big for loop finishes running, we should have updated parameters that help us reach a better set of parameters that reduce the loss, right? Or our error in our model, which in this case is a linear model. So that's that. Okay. So now I'm going to do problem 13. Okay. Great. So we did that. Okay. Let me just get water really quick. Okay. So let's see. Now, I think I solved those problems, or this problem before, but it's been a while, so I want to write a Python function that calculates the determinant of a 4x4 matrix using Laplace expansion method. So we want to implement this function recursively. Okay. Okay. I see what's going on. Yeah, okay. So what we're concerned with is, what problem is this? Problem 13. Okay. Let's let A. So let's say we have a matrix A, which is a 4x4 matrix, as shown as such. Then let's say this is A, B, C, and D, right? Then it would be the determinant of A would be equal to, I think, A times the determinant of a 3x3 matrix, which would be okay, so let's say that's red, minus B times the determinant of a new matrix, a new 3x3 matrix, which would be and then it would be plus C, which is the determinant of this matrix. Minus D times the determinant of this orange matrix, where these denoted colors are a 3 by 3 matrix. And then we want to recursively do that. So let's say we have the determinant of this. So let this color red be equal to some 3 by 3 matrix. 3, 1, 2, 3, 1, 2, 3, right? And let this be x, y, z, okay? So we have this equation. Then we need to find a way to calculate the determinant of this, of each 3 by 3 matrix. Well, this would be x times the determinant of okay. Let's say we have this brown color right here. Minus y times the determinant of and each of these colors would be a 2 by 2 matrix. Oh, that's a bad color. Let's make this gray. Okay. And then we know what the determinant of a 2 by 2 matrix is, right? So let this color equal some 2 by 2 matrix. Then let's say it would be A, B, C, D, right? Then the determinant of this right, since this is a recursive method, right, our determinant would be equal to this would be our base case, right, where we can actually compute a determinant. So it would be A times D minus B times C. So this is essentially Laplace's expansion. I mean, I think the actual yeah, I mean that's what it is. There's the mathematical formula where each of these are actually called a cofactor. But I just think of it like this way. So let's actually code this up, right? I think, so recursively, our base case, right, would have to be this, where the, whatever our square matrix, input square matrix is, right, if the dimensions are equal to 2. So, length of matrix is equal to 2, right? So it would be if the length of our matrix, the 2, right, then we just return, right, A, which is just matrix 1 or 0, 0 times matrix 1, 1, and then that minus matrix 0, 1 times matrix 1, 0. Okay, so yeah, let me just do that. So this is our ultimate base case. Now we'll have another case where if the length of matrix is equal to 3, right? Then we'll need to write this equation where we write x minus y plus z, and we recursively define what the components are. Okay, so let me think, how do we do this? Because like the issue isn't writing x, y, and z and like writing the mathematical expression. The issue would be finding a way to recursively construct these mini matrices within the actual matrix. So okay, we can have a, I'm thinking we can have a helper. So if we, I think the helper can be some function that constructs whatever the smaller matrix is, and then there can be a condition where like if we're equal to the certain column that we're on, then we just skip that, right? So it would be construct matrix, right? And then we'll obviously input two things: the current index that we're on, and okay, well, we need two things: matrix, which is just going to be a list either in int or float. And we're also going to need index, which is just an int, and it's just going to track where we are, and then we'll return another matrix. Yeah. Okay. Oh wow. Hold on, I think my live messed up. Actually is, or yeah. So yeah, information for. Okay. So what would that be? Well, for any n by n matrix, okay, so let's say we're on this current index. We want to start from 1 all the way to the end. So it would be, okay, it would be mini matrix is equal to this for length of matrix, sublist is equal to this if for C in range length of and we have to start at 1 from the row. Okay. If I is equal to, if it's not equal to index, right, then sublist dot appends matrix RC. Then we do mini matrix dot append sublist. And then we return our mini matrix. So this should work for any n by n matrix that we're actually given. So okay. Right. And then we do determinant is equal to 0. So now that we have this helper method, now we can actually write the equation for this. So it would be how would this work? So we start at this, we iterate through the columns, or iterate through the row for index. What would it be for okay, so I think it would literally be for I in range, the length of the matrix. We do determinant plus equal to, it would be -1 to the power of I, right? Because the first term would be positive, the second term would be negative, and then the third term would be positive again. So we would need that. And then the equation is also, we multiply by the respective determinant. So times determinant of 4 by 4, which we recursively call, of construct matrix and I. We'll, for readability, we'll call this variable index. And let me think. Oh yeah, we also need another term, which is our actual value, right? A, B, C, or D, or X, Y, and Z, depending on what the size of the matrix is. So we need matrix 0, index, and we know that we're starting from 1, so we're constructing the right things. And I think this actually works for I think this works for any size too, so we don't need this specific condition. We can literally just do else. And I think this works. And then we just return the determinant. So let me run through this code again. But this should work. Okay, so our base case is if the length of our matrix is 2, then we return that. That should be right. Otherwise, we'll set a determinant equal to 0. And then for the index and range of whatever that is, we'll iterate through the length of the matrix. We'll add -1 to the power of whatever its current index is, so then we're alternating between adding and subtracting. We'll multiply it by our top value of the matrix, which is just 0, and then our current index, and this, and this, and this. And it works for any size. That should be fine. And then we also multiply it by our actual determinant, which is a recursive call to our constructive matrix, assuming that this works. So now let's look at this construct matrix. So we're given a matrix and we're also given an index, right? Because we need to know when to skip, right? That certain value. And we return a smaller matrix. So we have a mini matrix, and then so for R in range, that starts in 1. So we start here and then we iterate until we reach the end of that length of the matrix. We do sublist. We create a sublist, and then the column in range. Okay, wait, no, not if we do if our current column is not equal to index, then yeah, then we append that element because we know we're doing the right thing, and then we append that sublist to the mini matrix and we return it. So this code I think should work. So let's see if it does. Hopefully. Line 15. Oh, I don't think I need that. Okay, let's see if this runs. Okay. No, it's not working. Alright. Why am I failing it? So we know the determinant is that 4 by 4. Oh, it's not -1, is it? Wait, no, it is. Yeah, no, that's right. Okay. Oh, wait, no, we're iterating through the column, so this has to be 0. Yeah, because it's 0 and then whatever that is. So then okay, so that's what the bug is. I think that's right. Okay, now what's going on? No, it's the same thing. Well, yeah, it wouldn't matter because it's a square matrix. Okay. Determinant 4 by 4. Am I calculating it wrong? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. We need to do this. So the specific example that they give. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so the calculation for this would be, okay, scientific. It would be, well, okay. It should equal, so the determinant of that one minus determinant of whatever that is. We know 1 times. And then it will be minus 2 determinant plus 3 determinant minus 4 determinant. Okay. Oh. Okay. Unless the math is wrong, right? The determinant of that would be 6 minus 7 plus 8, 16, 11 times 16 minus 12 times 15. Something wrong with my stream. Okay. 10 times 16 minus 12 times 14. Okay, I don't know if I'm doing that right. I don't want to type that out. What am I doing wrong? the length we added. Wait, am I not doing it right? Zero index. Index and range. Two, three. And we have our current matrix. Unless this is not right. For R in range. Wait, so for each row, I'm starting at 1, then I iterate starting from index 0. If C is not equal to the index that I'm passing in, then yeah, I append the right value. And then I append that sublist to the matrix. So I use my hint. Oh my god. Wait, no, I think I got it. Okay. Oh, okay, so, because I don't account for the case where I'm constructing a new matrix in a non-starting 0, or on an even index. So then it's saved in the suit, and it starts with it starts with subtraction. Like, if I'm on B, and then I'm on D, it will start with subtraction when calculating the determinant instead of the opposite. So, okay, so then that should be the bug, but then how do I fix that? Okay. Okay. Then okay, this is probably bad code, but I would say like if index, so if I start at an even index, right? Then factor is equal to minus 1 to the power of index. But if it's odd, then I do factor is equal to negative 1 to the power of index minus 1. Right. So, wait. How about hello? Yeah. I'm gonna get barbecue with friends later. Or like they're yeah. Yeah. Okay. I need to turn on lights. Okay. Wait, no, I don't think that's right. I don't think that's changing anything. Okay, so the hint says that and Laplace's expansion should be alternating, but your code uses negative 1 to the index. Okay, but is that not what I do? Unless no, I don't think that's gonna change anything. Oh, okay. Wait, so my code was right. That's so weird. So then I'll just do this. Yeah, okay. So if I walk through the code, yeah. So the base case of this, right, would be if the length is 2, then then I just return the standard determinant. Otherwise, then I create a new determinant, and then I do use Laplace's expansion, where I write a function to construct a mini matrix that corresponds to wherever I am currently at, or where I'm currently at when I'm iterating through the matrix. And that gives me my answer. Okay. So I'm gonna save this code and I'm gonna reset and I'm gonna see if I can do it again. So the base case, right? If the length of matrix is equal to 2, then I just return matrix 0, 0. Column. We multiply that by C. We also multiply that by determinant of 4 by 4. C. Determinants. And then, so now we actually have to write the function that constructs the mini matrix, which takes in a list of lists, and then index column, which is just an int, and that returns us a list of lists. So C is not equal to call, then sublist dot append matrix RC, then me matrix dot append sublist, then return the me matrix, and that should be it. Yeah, that's a pretty cool problem. Yeah, at least I understand the concept there. Okay, now let's see if I can do singular value decomposition. Okay, so now we do SVD. We're going to write a Python function called SVD that finds an approximate singular value. Decomposition of a real 2x2 matrix using one Jacobian rotation. The input A, a NumPy array of shape 2, 2. You may use basic NumPy operations, matrix multiplication, transpose, element-wise math. Do not call NumPy, Lineage SVD, or any other high-level SVD routine. So stick to a single Jacobi step, no iterative refinements. Return a tuple that returns us the factors of whatever matrix we're conducting SVD on. Reuse a 2x2 orthogonal matrix. Its length to NumPy. Okay. Alright. Me. Okay, let's look at geeks for geeks. So first we need to compute a, right? So we're given A. So first compute A dot T. Okay. Then we need to find the eigenvalues of A, T. We know that's a 2x2 matrix. Okay. And does it have to be in descending order? Find the right singular vectors. So, what problem is this? Let me save my code. This is problem 12. So, SVD. So we need to return a tuple that contains U sigma V T. Yeah, okay. So we'll contain U, sigma, and then VT. Okay. Where A can be broken down into VT. Okay. Find the eigenvalues. Find the right singular vectors. which is the eigenvectors. And then just matrix U. Formula. Okay. Oh, so is it just parentheses? Okay. Python. Oh, okay. So I guess I can just create a list first and then initialize it. Okay. Which is that tuple. Okay. So okay. So the first thing we need to do is compute so we need to compute a times A transpose. But how do finding the eigenvalues actually? Okay. Oh, okay, so the singular values are the square roots of the eigenvalues. Wait. It's the eigenvector corresponding to lambda. There's a right and left eigenvector. Is equal to 1. Plus 2b. Oh, okay. So, I see. That's how you do it. Since it's a 2 by 2, it's just a system of linear equations. Okay. And then we find the right to the eigenvectors, right? We compute the left singular vectors. What was sigma? It's the singular values of A in descending order. Okay. So we'll use this information. Okay. So based on the documentation from Geeks for Geeks, then we're given the formula on how to find on how to find this. So dot T. Okay. So Geeks for Geeks tells us how to find U, and we'll go based off the definition on like the extra information that we find to find sigma and then the transpose of V. A in descending order. Singular values. which is just matrix U. U. M by M orthogonal. Compute and add U to list. Then using find sigma list, and then we need to transpose okay, so Jacobi rotation. From A to symmetric, because form the right singular vectors of A. Okay, I'm gonna save my code. I'm gonna reset. Compute A. So from our old problem, a plus d. Quad b is equal to plus So now we know the eigenvalues of that. So it's just E2. So I would say E1I to it's AT. I. So then now we're given C1 and C2. Okay, no, I might just go with so we want to find this first, right? So A2 is equal to So to diagonalize B, we seek a rotation matrix such that the optimal angle is this. Which now satisfies okay. So we need to find R, which is a rotation matrix. Okay. B1 equals B2. NumPy dot pi. Okay. So NP pi dot pi divided by 4, 0.5 times NP dot arctan 2 times 0.1 divided by B 0.0. Okay, so that should be my rotation matrix. So then now D is equal to R dot T Okay, so now we have D, and now we have to extract the singular values. Diagonal entries of D P dot square root D00 U Oh my god. Array R dot T. Please work. Where's my indent? Wait. Return arrays must be of array type. Okay, I think I have to Okay. I'll probably return to this problem later. I don't know. I'm struggling with it. Okay. Yeah, I think that's pretty much it. It was like 2.5 hours, but I think I got a lot done. Yeah, I'll see you guys next time. And I'll get to it next time as well.